The last talk of this session is from Georgetown University, James Friedrich. And should we trade off higher level mathematics for abstraction to improve student understanding of quantum mechanics? Should we?
Yes. Well, I'm going to tell you that you should. Whether or not you agree with me will be up to you. Thank you very much. It's a pleasure to be here. This is the first time I've been at ETOP, and I'm a physicist, not an engineer. But what I'm talking about is very relevant for engineers. But before I start, I have a number of colleagues who are in Ukraine, and I start every one of my talks with a moment of silence, given what's happening in Ukraine. Thank you very much. So how should we teach quantum? And here I really want to focus on the notion that the regular quantum course, which is, I think, absolutely critical for someone who wants to understand and work in quantum sensing, to be able to understand traditional quantum mechanics. The question is, how should we teach it if we want to be doing this for people who aren't physicists? So historically, there are two choices. You have Heisenberg's matrix mechanics, which really isn't taught at all. We do teach quantum mechanics with matrices, but it's not the way Heisenberg did it. Or there is Schrodinger's wave mechanics. But I want to argue that there's actually a third way of doing this. And this was actually first developed by Pauli when he solved hydrogen in what people call a matrix mechanics solution. But I'll explain to you why that isn't really matrix mechanics. It was really promoted by Dirac, and then it turns out Schrodinger, the same guy who did the wave equation, reformulated quantum mechanics in 1940 to work in this fashion. And when you work with operator mechanics, you're working in a representation-independent way of teaching quantum mechanics. So in an introductory physics class, we spend a lot of time teaching students that don't think of the vector in terms of its components. Think of it as an object that lives by itself. I can represent it in terms of its components, but it's an object, an abstract object that sits out there. We get to quantum mechanics, and what do? You have to work in coordinate space. There's a real disconnect there. So I'm telling you that you don't have to do that. But when we do this, this really lowers the math load. No differential equations, no Dirac delta functions, almost no matrices, and everything follows from four fundamental identities: the Leibniz product rule for commutators, the Hadamard lemma, Baker-Campbell-Hausdorff formula, and something called the exponential disentangling identity. I'm not going to be using this, so I won't talk about this. Hadamard lemma is that infinite sequence, e to the a, b, e to the minus a is an infinite sequence of nested commutators. Baker-Campbell-Hausdorff is e to the a, e to the b is e to something, which is a long series. Okay. But of course, this is abstract. So I'm going to illustrate for you how you get the harmonic oscillator wave function abstractly via operators, no differential equation. Now, I do want to prepare you for this because this is something you're not familiar with. This is a new thing about the harmonic oscillator that you're going to see here probably for the first time for most of you. And it is very easy to confuse unfamiliarity with this is too hard. So I'm going to try to ask you not to make that conflation and instead focus on the fact that all we're going to use are commutators, eigenvalue, eigenvector relation, and multiplying by 1. That's all of the elements that go into this. However, you're going to look at this and at some point your eyes might glaze over. So hopefully I'll keep you grounded during this. So the standard treatment, of course, we start with the Hamiltonian, which can be factorized in this form as A dagger A with the standard lowering and raising operators, the raising operator being the Hermitian conjugate of this. The energy eigenstates are given by A dagger raised to the nth power, 1 over square of n factorial for normalization, and then the ground state satisfies the A operator acting on it annihilates. So this is something everyone should be familiar with. So I'm actually highlighting all those in red. And now we use this Hadamard lemma, which is taking this exponential of an operator, exponential of a negative operator, and this operator in between. You expand it in power series, and it stops after the first term because x squared commutator with p is an x squared commutator with x is 0, so there are only two terms, and indeed the two terms are exactly these two terms. So you trust me that I got the numerical constants right. You can see that this is just a different way of representing these raising and lowering operators. Now, you can use this relationship here using the similarity transformation for the lowering operator to recognize that this says exactly the same thing as this. It says the P operator, momentum operator, acting on this combination of an operator acting on the ground state is equal to 0. If you think in terms of quantum mechanics, this is a state that has 0 momentum because the P operator acting on the state gives me the P eigenvalue, which is 0 acting on the state. So this is actually a 0 momentum eigenstate. We're not going to actually be using that property, but we will be using the property that the momentum operator annihilates. Okay, so we start from the energy eigenstate. We're going to replace the A dagger with this similarity transformation. And now because you have this operator sitting right next to this operator, when you have a power of these A daggers, you can see those two operators cancel, and the only ones that are left are the ones on the outside. Now, the next thing that we're going to use is we're going to use the fact that this P operator annihilates the state with a plus sign and a 2 in the denominator. But here I have a negative sign with a 2 in the denominator. So I do a multiply by 1 to recreate this as an exponential with twice the exponent and then with a positive. The P operator annihilates this part. But now since a P operator acting on this gives 0, I can take a P operator acting on this whole thing and replace it by a commutator, because the term that I'm adding has a P operator acting on this state, but P acting on that state is 0. So you can do that and repeat it for every one of those P operators, and you get a nested set of commutators of momentum with this operator in the center, and then you still have this Gaussian operator sitting next to the harmonic oscillator ground state. Now, those of you who are familiar with Rodrigues formulas, if you want to just think in your head, momentum is derivative, you can see this is a n-fold derivative of a Gaussian multiplied by a Gaussian with the opposite factor. You might say, oh yes, Rodrigues formula tells me that's a Hermite polynomial. Indeed, you can show that this set of operators is a Hermite polynomial operator of x acting on this state. Okay? You just do that by figuring out what H0 is, what H1 is, and then showing the recurrence relation between them. It takes a little bit of algebra. I'm not going to show that one to you. Now, to get the wave function, I have to multiply by the position bra. So we just multiply the position bra. But you see, this is an eigenstate of this operator. So I can just let this operate on here, replace it by the eigenvalue, and move it out of the expectation value. And so there's my Hermite polynomial. And now I have to calculate the ground state wave function. How do I get the ground state wave function? Well, here I'm going to multiply by 1. I want to create this state that's annihilated by the P operator. So I have to multiply by an opposite Gaussian. Then I can let this act on the state as well. That will pull a Gaussian factor out. And now I'm going to evaluate this. To do this, I have to rewrite the position eigenstate in terms of the translation operator acting on the state at x equals 0. So I'm going to do that, and you see the translation is with the P operator, but the P operator annihilates against this. So this exponential operator gets replaced by 1. And it's gone. And now this Gaussian operator can act on this state because this is the eigenstate at x equals 0. So I replace the x operator by 0. That one is gone, and I'm just left with a normalization constant. You can see this is the harmonic oscillator wave function. Modulo the normalization constant, Hermite polynomial times a Gaussian factor. So, of course, to get this, you have to do calculus and do an integral. It's just a number, and if you wanted to do this completely without calculus, you just have to tell them what the number is. And there you have it. We've gotten the harmonic oscillator ground state using just algebra, multiplied by 1. We also did adds by 0 to get the commutators, and working with commutators. So how do you promote this kind of abstraction with students? Well, you don't start off your course doing that. You're going to lose them immediately, okay? But you work up to it, okay? All right, so how do we do that? We start with concrete things, we add the formalism, and then we add the abstractions. You have to build up students to have the ability to work with this abstraction. I include writing assignments in the class to encourage the students to think more deeply about the concepts and the abstractions. And we provide multiple attempts on questions to allow students to think more deeply on the material. For those of you who are aware of different kinds of decision-making theories, this is promoting the process 2 versus process 1 in dual process theory. Now, using abstraction lightens the mathematical prerequisites. You can see we didn't need calculus to get a wave function, even though you've normally been taught that's a solution of a second-order differential equation, and you have to solve it with a series solution. And that in and of itself cuts out a whole bunch of people who are never going to be able to follow what it is that you're doing there. Now, this allows us to now cover more physics and more experiments in the quantum class because we're not spending a lot of time teaching them math. So, this one semester course, these are the kinds of experiments I cover. Amu-Mandel, I cover Stern-Gerlach, delayed choice, Hanbury-Brown and Twist. We look at key distribution, high precision, Pickering-Fowler lines. I do quantization of light, so we look at heterodyne, homodyne detection, time of flight to measure momentum, and so forth. I do this all in just a one semester class. So we found that this works very well with students at Georgetown, and it's also available as a MOOC. I've taught people all around the world this material in this fashion. And I'm going to now just conclude and leave time for questions if you have any. I'm going to thank the funders here. And if you're interested in additional information, this is a website at Georgetown that covers most of the material that I've been doing on teaching quantum pedagogy. The undergraduate course is this course here on quantum mechanics. And then there's also a course that is a shortened version of this course called Quantum Mechanics for Everyone that focuses just on conceptual ideas. That's a 6-week course that actually is going to be offered starting June 15th. If you would like to see what this is like, feel free to come and join the class. And with that, if you have any questions, I'll be happy to answer.
Time for a couple of questions.
Question, is your class free or we should pay for this?
So the quantum mechanics for everyone, so there's always an audit facility on edX classes. So, but they require us not to give all the content for free. The quantum mechanics for everyone class is grandfathered. So actually you can take that entire class for free. The undergraduate class, if you want to see the problem sets and things like that, costs $250. However, if you want to see the stuff and you don't want to pay the money, you could just send me an email and we can work something out.
The derivation you just gave is a derivation for the harmonic oscillator.
Yes.
What would one do with this operator algebra if you have a general situation?
So it's not clear exactly how you would use this for an arbitrary potential, but we don't solve arbitrary potentials. Every single problem that we solve in a quantum mechanics class, including particle in a box, Coulomb wave function, isotropic harmonic oscillator, and so forth, they all can be solved in this way. That's what Schrodinger did in 1940. Many people are not aware of this, but you can use operators to solve all
how
those
do you do it for
problems.
particle in a box? How do you do it for a particle in
You
a box?
factorize it as an A dagger A. You have to use trig functions to do that, and you get.
Well, isn't that mathematically more sophisticated than the differential equations that the students learn in other courses?
So again, I would say no, because it's factorization, it's algebra, it's actually high school level work that you're doing. It's trigonometry and algebra. So I would say no, but it's exactly unfamiliar. And so you might at first think, oh, this is just totally different. There's no way they can get it. But if you look at the math that's actually used, it's quite a bit lower level than differential equations. You don't need calculus.
Which time you spend preparing them operators before you go on down this?
So I spent 4 weeks of my class doing conceptual things with high school level math, covering superposition, entanglement, a thing that I call tagging, which is creating entangled states reversibly, measurements, and complementarity. And after students have those ideas firmly and grasped, we start introducing Dirac notation And then we started introducing operators for spin, motivated on Stern-Gerlach experiment, saying there's an operator that corresponds to the result of the Stern-Gerlach experiment. And then there's an operator that allows you to take you from one of those results to the other one, an S plus operator. Having the S plus and the SZ is all you need to get the SU2 algebra by working out what it has in the state. That is probably around week 6 that we're doing that. And then we just start moving into creating position momentum states and harmonic oscillator, and we go through everything. So, but in the last week of the class, I do second quantization of light, and we cover light. And so this is all in one semester class.
Thank you very much. So this ends our session. Well, one more question.
What kind of profiles do you find for these PPX schools in terms of regions and background?
I have high school students taking the class. Most of the students who take it are retired professionals, engineers, doctors, things like that. They're all around the world. I think the top country represented is the US. I think number 2 is India. Canada, England. There was one time where Brazil had a pretty high representation. So it's all over the world. Yeah.
Cool question. So there's definitely some historical reflections here to what you're doing there. I'm wondering, what's your take on how important it is in everything what we discussed to actually go back to the past and see what Friedman did? Because there's the whole series of the elections. Should we really be introducing those kinds of aspects into these curricula that we're talking about, like Feynman's lectures and certain derivation, but surely would that help us?
Well, I'm not really sure. I mean, in many respects, this first part that I said uses no math aside from high school and stuff like that is actually solving everything by path integrals. Now, we don't tell them that you're solving it by path integrals, and we're doing a simplified approximation to path integrals, but that's essentially what we're doing. So by taking this class, you're actually getting exposure to techniques related to path integrals, in addition to working with operators and other things like that. The techniques that we normally teach, series solutions and this and that, almost never enter into any research problem afterwards. But working with operators, if you're going to go on to quantum field theory, now I'm talking with a physicist hat on, you're going to go into quantum field theory, working with operators, having a good sense of operators and what kind of manipulations you can do with them, very valuable. You're going to go into solid state physics, many-body physics, very valuable. You're going to go into quantum optics, really valuable, that you've already seen quantization of light and so forth. So I think there's a lot of inertia built into the way we've been teaching quantum mechanics that we need to try to find a way to get over and start introducing these more modern ideas and concepts into the classroom.
Thanks again.